All right, so moving right along, we're now going to get still talking a little bit more about heat and whatnot. We're going to talk about a calorimeter. And kind of a crazy word, calorimeter, sounds pretty dangerous and something that might be a little bit alarming. But all that a calorimeter is a tool used to measure heat transfer. All right, so tool used to measure heat transfer. There are high-tech calorimeters. In our labs, we're going to be doing a lab dealing with calorimeters. Basically, we can use a styrofoam cup. Styrofoam cup, why styrofoam? Because it doesn't allow a transfer of heat to the surroundings, the air around you as easily. You know darn well that if you have a styrofoam cup and you put hot coffee into it, you can probably hold that styrofoam cup, drink your coffee, as opposed to putting that same exact hot coffee in a glass cup and try to hold that glass or whatnot. It's going to be a lot hotter. And so that styrofoam is an insulator, and it does a good job of kind of keeping the heat of the reaction inside where it's reacting in the calorimeter. So a couple of things we need to recognize about, or what's important when we start talking about calorimeter use, is that the Q, the heat, right, of the SUR, and the heat of the surroundings, let me write that down below. The heat of the surroundings is equal to the heat of the reaction. The heat of the surroundings is equal to the heat of the reaction, but opposite in sign. Okay, now obviously if the surroundings is a negative value, then the heat of the reaction will be a positive value. But again, whatever the surroundings gets, let's say from the reaction, if the reaction releases heat to the surroundings, then whatever the surroundings get is what the reaction gave. I always do a little analogy. If I take out a $20 bill and give it to someone, I'm going to be minus 20, someone else would be plus 20. So it's the same type of thing with heat. If you have a reaction taking place and you put something in, whatever that heat that's being released is going to be the same that the surroundings gets. Okay? So let's take a little bit a more detailed look at this. Okay? If I say we're going to do a reaction kind of with a calorimeter, we've got a calorimeter with some water. Okay, here I have some water, and I have 50 grams of water. Can you see the blue? I think you can. 50 grams of water. I could say, as a matter of fact, just so that I remind you all, and often I will do this, if you have 50 milliliters of water, okay? Obviously, the only little wrinkle here is to remind you that the density of water is 1, so that if you have 50 milliliters, you have 50 grams, okay? And if I say that if that 50 milliliters, we take a temperature of that, and it's 20 degrees Celsius, room temperature water. And we also know our specific heat of water, right? 4.18 joules per gram degrees Celsius. All right? If we heat up a chunk of iron, okay? So here's some iron. We hold it in a flame. All right? Here's some iron. We're going to be actually doing this in our lab. So here's some iron. We hold it in a red hot flame and heat it up, okay? And we get that iron to 120 degrees Celsius. It wouldn't take much. Temperature of the iron is 120 degrees Celsius, okay? And I take that hot flaming iron and I dump it into my water. Well, what's going to happen? The iron's going to cool off and the water is going to heat up. All right? So if we say that the water heats up to 40 degrees. Okay? So this water now is 40 degrees. This is after you put the thing in. Okay? And another thing that you would need to recognize or know would be the specific heat of iron. The specific heat would be 0.448 joules per gram degree Celsius. So let's see where we're at. We got a piece of iron. We heated it up in a flame. We had it measured at 120 degrees Celsius. We put that hot piece of iron into water that was at 20 degrees. That hot piece of iron increased the water's temperature to 40 degrees. Okay? Now it is important that we realize that the water went from 20 to 40, but the iron is also finishing at 40, right? It started at 120. Its final temperature is 40 as well because the iron's sitting in the water. Okay? So with that being said, I could ask how many grams, or in other words, the mass of iron did we have? All right? Now what I want you to understand is this. Basically what we're going to be doing is using that Q formula twice. We're going to use it twice, and we're going to use the fact that the Q of the surroundings is equal to the Q of the reaction. So Q of water is equal to the mass of water times the change in temperature of water times the specific heat of water, right? And the same thing goes for my iron. The Q of the iron is the mass of the iron times the change in temperature of the iron times the specific heat of the iron. Now, before I go ahead and solve this, let's see what we're given. We have the mass of the water because we have the 50 milliliters. We have the change in temperature of the water, and we have the specific heat. So that means that the only variable we don't know is the Q of the water. We don't know the Q of the iron. We don't know the mass of the iron. We do know the change in temperature and heat. So notice that the iron Q and mass has two variables that are unknown, whereas the Q of the water has only one. So if we calculate for the Q of water and know that whatever the water got was what the iron gave, then we'd know the Q of the iron, and then we'd have an ability to solve for the mass of the iron. So let's go ahead and do that. So let's grab a different color, white. All right, so to solve for the Q of the water, it's going to be the mass of the water, which is 50 grams. The change in temperature of the water is 20 degrees Celsius. And again, it's not this value, it's the fact that it went to 40. So 20, it just is a 20. Times the 4.18 joules per gram degree Celsius. Okay, I multiply those three and I get the Q of the water is 4180 joules. Now, because the Q of the water is that, then that means that the Q of the iron is negative 4180 joules. So I now have this. So if I want to solve for my mass, and I'm going to actually, let me move this over here a little bit because I know my head's going to be in the way, but negative 4180 joules. Okay? I'm going to rewrite this formula solving for mass because that's what we're solving for, right? We're solving for the mass of the iron, which is going to be the Q of the iron over the change in temperature of the iron times the specific heat of the iron. Again, in order to get that, I divide both sides by change in temperature times S. That gets rid of it on that side, makes mass all alone, and so we can get the formula that way. So the mass of the iron is going to be negative 4180 joules over the change in temperature. Notice that it went from 120 to 40. So that's a negative 80 degree temperature change. Specific heat of iron, 0.448. I'm running out of room here. I do the math, multiply the bottom, then divide the two, and I get the mass of my iron is equal to 116 grams. So again, how did I use this? How did I solve it? I knew that the Q of one is equal to the Q of the other, just opposite in sign. I had two Q formulas. One was the water, one was the iron. And I'm a really big fan of taking the little extra second to write all these subscripts. Okay, just so you don't get confused as to what number we might be using. But so by knowing how much the water went up and knowing how much the iron went down, we can determine what the mass of the iron was. So that's how you can calculate a calorimeter type of question.